Namaste. Welcome to this channel, Dr.ARM'sChemistry. Chemistry. Last time we were discussing general properties of transition elements, and today we will see next part of this, that is coordination chemistry. Coordination chemistry. So, first point of this coordination chemistry is electroneutrality principle. Electroneutrality principle. So this is given by Pauling, and according to this principle, this method is used to estimate the charge on complex and every atom present in the complex or molecule. So this charge, according to this principle, must range between +1 to -1, +1 to 0 to -1. So the atom in this complex or molecule may have maximum charge ranging between this, that is +1 to -1, and it should be close to 0. So this can be explained with suitable example. We can consider the example of, say, CO NH3 6 3 plus. We can consider this example. So here this example can be represented in different ways depending upon the type of bond here. So first type of example can be represented in this. Say this is cobalt, metal ion at the center, and here is NH3 molecules. These are NH3 molecules coordinately bonded to central metal ion like this, and this will have a +3 charge. This will have +3 charge. Say this is structure A. Now there is another structure in which we are considering the metal ion is at the center and the NH3 are bonded to central metal with covalent bonds. These are coordinate bonds. Coordinate bonding. Here it is covalent bonding. So this is structure B. You will find that this structure has charges, say +1, +1, +1. This is +1, +1, and +1. So every ligand after covalent bond formation shows +1 charge, and here cobalt shows the 3 minus charge. So in this way, the structure D is covalent. Now we will consider another structure, that is cobalt, and there are NH3 molecules surrounding it like this. And these are ionically bonded to this cobalt with 3 plus charge. So these are ionically bonded. So we can say this is structure C. This is 100% ionic bonding. And this is covalent bonding 100%. Now another is cobalt is at the center and it is bonded to NH3 molecules. Like this. Here the molecule is electrically neutral. So the charge on the central metal ion is 0, or the charge here on the central metal ion is 0, and each ammonia molecule has plus 1/2 charge, plus 1/2 charge, like this. So this is structure D, and it is 100%, no, and it is not 100%, it is 50% ionic, and it is 50% ionic plus 50% covalent. So here we are having 4 structures. The structure A shows it is covalent. Coordinate means here we are considering coordinate bond, means electron pair of nitrogen is shared with this cobalt at the center. So 6 ammonia molecules share their electrons with this cobalt, as a result of which the electron density is strongly increased on central metal atom, and thus total molecule possesses 3 plus charge. So this is coordinate bonding model. Then second is covalent bonding model, that is 100%. So here the nature of bonding is covalent, means 1 electron of this cobalt and 1 electron of this, means there are in all 6 electrons, means 6 electrons are supplied to this cobalt, and 3 electrons are shared, or maybe this cobalt is in the 3 plus state. So in all, out of 6 electrons, means actually there are 3 electrons expected to be shared with this cobalt, and that is why it gives 3 minus charge. But this structure is not realistic. This is unrealistic structure which gives a covalent bonding model. Then this is ionic model in which cobalt metal is at the center, and these are electron rich species, that is ammonia. So there is ionic bonding. So there we have not shown any line or a bonding actually, because it is ionic in nature. Then the last is this cobalt is at the center, and all these ammonia molecules. Here we know that the structure has three plus charge. So all these are having 3 plus charges. So in this structure, every NH3 is expected to contribute, means out of 6 electrons, so out of 6 ligands, only 3 ligands, means at a time 3 ligands are, or in other words we can say these 6 ligands supply 3 electrons to the central metal atom, and central metal ion is in the 3 plus state. So after receiving 3 electrons from these 6 ligands, the molecule gets neutralized, or the central atom gets neutralized, but the residing residual charge on this complex is 3 plus. So this type of structure shows 50% ionic bond and 50% covalent bond. So the charge distribution is shown here, which is having plus 1/2 charge on the ligands as well as the 0 charge on central metal ion. So this type of complex structure is observed experimentally in aqueous solution. Hence, the extreme bonding model is not possible. Means the complex is neither extremely ionic 100% or 100% covalent, but the molecule is having 50% ionic nature of bonding and 50% ionic nature, covalent nature of bonding. Means 50% characters of each type are available. So here another example, we can see another example, MPCl6, or the only complex ion is ApCN6 3 minus. ApCN6 3 minus. So here a realistic charge distribution results in each ligand carrying a charge of -2/3. So if we see the structure, we can draw it like this. Fe is at the center, and the Fe is bonded to Cn minus ligands like this. So the experimental results shows that the ligands Cn minus are carrying -2/3 charge, -2/3 charge each, -2/3 charge. So if we calculate how many charges are there on these ligands, that is -2/3, and total number of charges are provided, supplied or shown here are into 6 by the 6 Cn minus ligands. So in all there are -4 charge on this -4 charge is supplied by the Cl- ligands, but the complex has 3- charge. So this Fe can have +1 charge on this central, that is central atom, metal atom. So 6 electrons are supplied by these Cl- ions. So these are providing 6 negative charges. 6 negative charges are provided by 6 electrons by Cl, 6 Cl- ligands. And the Fe gives back 4 electrons, as a result of which the resulting charge is +1 on Fe. So this back bonding is taking place through d pi p pi bond. D pi. So this has d pi and these have p pi orbitals. Means metal ion Fe provides d orbitals of pi nature and Cl- containing carbon provides p orbitals of pi nature, which gives back the excessive electron density on Fe ion. As a result, it gets stabilized. So in this way, the charge distribution is observed in order to show the complex to be neutralized, and the maximum charge density, or we can say charge distribution on any atom, should be between +1 to -1, or it is close to 0. So this is about this electronegativity principle. We will stop our discussion here. Thank you very much for watching this. Please subscribe to this channel and press the like button and bell icon. So thank you.